This is part 19 of the series Applications of Differentiation. In this part, we're going to look at a concept called differentials. In the last section, we were introduced to the idea of the tangent line approximation to a function, and we used those in conjunction with Newton's method to find the approximations to zeros of functions that were difficult to find otherwise. In this section, we're going to extend that idea of tangent line approximations to functions, and we're going to generalize it into a form that allows us to approximate functions with even greater application. So the first idea in differentials is the idea that the tangent line at some point C is an approximation to the function f at some point C within the local region of C, within some small distance away from C. And so we start out with the point slope form of a line to generate our tangent line approximation to this function. And to that, we have to add our first y value is the function f evaluated at point C. And then we need the slope of this tangent line, and the first derivative gives us the slope. So we take the first derivative of the function evaluated at that point C, and that gives us the slope of the tangent line approximation at C. And we have this quantity x minus c, which is the distance from any point x from C within that local region around C. And so when we solve this equation for y, we have the tangent line approximation to the function f at point C. So that's what this equation is here. Now, when this equation is used as an approximation to the function at some point, this quantity x minus c becomes what we're going to call delta x. That is, the change in x from C to some other point x on the local vicinity of C. This gives us this equation. It alters the tangent line approximation to this equation, which tells us the y value, this y value on the tangent line approximation, is equivalent to the quantity f of c, the function f evaluated at C, plus this quantity here, which is f prime of c delta x, which adds on this piece over and above the tangent line approximation at C. Now we're going to switch our attention over to the actual change in y from f of c to f of c plus delta x. So f evaluated at c plus delta x here. So this actual change in y is given by this delta y, and it is this quantity minus this quantity. So again, this actual change in y due to the additional delta x value evaluated at the function is equal to f of c plus delta x, the value of the function evaluated at c plus delta x, minus the value of the function evaluated at C. And so we have that expression here. And so the whole idea of differentials is wrapped up in the idea that this actual change in y from here to here can be approximated by this change in y to the tangent line approximation when this delta x value is arbitrarily small. So we can say that this actual change in y, this delta y value, is approximately equal to this f prime of c delta x, this approximated change in y, when the delta x value is small. So to summarize, when this expression, delta y is approximately equal to f prime of c delta x, is used to approximate the function, delta x, this delta x value, is called the differential of x, and we denote that as dx. So this term in the approximation, f prime of c delta x, is transformed into this expression, f prime of x dx, and we call that the differential of y. And we denote that whole thing as dy, and that brings us to the definition of a differential. So the statement of the definition of differentials is if y equals f of x represents a function that is differentiable on an open interval containing x, the differential of x, dx, is any non-zero real number, and the differential of y, denoted dy, is dy equals f prime of x dx. Now hopefully this will look familiar to you from our derivative expressions, because we were using things that looked like this. If we have dy over dx, we also called that f prime of x. So you can see that this differential is a restatement of what we've been dealing with in differential calculus all along. Let's go ahead and look at some applications of differentials. So we have this function y equals x squared, and we want to find dy when x is 1 and our dx, our approximated change in x, is 0.01. So we know that the differential form dy equals f prime of x dx. So f prime of x is 2x, and so dy is 2 times x is 1 times dx, which is 0.01, which gives us approximately 0.02. Now let's compare this value with the actual change in y. The actual change is delta y, which was f of x plus delta x minus f of x. So this gives us f of 1 plus 0.01, because that's our delta x, minus f of 1, which is 1.01 squared, substituting in here, minus 1 squared, which is, so you can see that our approximation is very close to the actual change. So when our delta x was relatively small, our approximation was almost the same. So let's move on to another application of differentials. Now this application of differentials is called error propagation, and the value of it is very important in many engineering and other disciplines where we're concerned with precision, whether it be in the dispensing of medicines or in tolerances for machine parts and things of that nature. So here you can see the expression for the actual change in y, and this delta y value is now being called propagated error. This x plus delta x is the actual exact value of our target item, whether it be a manufactured part or something of that nature. And this delta x becomes a measurement error, because we can only measure as good as the instruments we're using to measure. And this value x in the f of x, this x value that we plug in here, is our measured value. So let's go ahead and apply this error propagation concept to a practical function. So in this case, the measured radius of a ball bearing, and in case you don't know what a ball bearing is, it's just a spherical, usually steel object that is designed to take the load of two metal parts that have to rotate with respect to each other. For example, an axle in a car. The car is moving laterally, but the axle is rotating with respect to the car. So this ball bearing has to take the load of the car pressing down on the axle while the axle is rotating inside. So that's what a ball bearing is. And so the measured radius of the ball bearing is 0.7 inches. If the measurement is correct to within 0.01 inch, estimate the propagated error in the volume of the ball bearing. So in this problem, we're dealing with volume, and a ball bearing is a sphere, so we're dealing with the volume of a sphere. So volume equals 4/3 pi r cubed. And what we're looking for is the change in volume. So dV with respect to the radius, dr, equals, we're going to differentiate this. So when we multiply, we have 4/3 pi times 3r squared. This simplifies to 4 pi r squared. And that's, of course, equal to dV dr. Now we're going to put this into differential form. And remember, differential form, dV equals 4 pi r squared dr. So in case you missed that connection, what we have is dy dx equals f prime of x. And we said the differential form is dy equals f prime of x dx. So this takes the place of our dx and comes up here. This is f prime of x. In this case, it's f prime of r. So this is our derivative, and this dv is our change in volume. So differential form, differential form. So substituting our values, we have 4 pi, our r is 0.7, and our dr is our error in measurement, 0.01. So this is approximately 0.0616, and that's plus or minus because this tolerance is either up or down by 0.01 inch. So this is our propagated error. Now, in looking at this number alone, it's difficult to tell if this is good or bad. And one way we can solve that is by doing a comparison. We can compare this propagated error with the actual volume. And so our propagated error is 4 pi r squared dr over 4/3 pi r cubed. And simplifying this, we can see the 4's are going to go away. This 3 is going to go to the numerator. The pi's cancel out. This r squared term is going to go away. We're left with dr over r in the denominator with a 3 in the numerator. So this is going to be 3 dr over r, which is going to be 3 times 0.01 over 0.7, which gives us approximately plus or minus 0.0429, which is 4.29% change. Or we could call that 4.29% error. So, after all, not such a bad approximation to our values.